Hello, this is Miss Moore, and today during chemistry we're going to discuss stoichiometry, specifically limiting reagents. Today's essential question: how is a limiting reactant in a reaction determined? For today's lecture, make sure you have your periodic table and calculators handy. Okay, limiting reagents, what are they? So all of the reactions and calculations thus far have described an ideal situation, a situation where we have the exact right amount of each of the reactants, and you end up with none at the end. However, there are chemical reactions when there is an insufficient or not enough quantity of any of the reactants will limit the amount of product that is formed. Okay, so you could end up with a reaction where you have a lot of one thing, a little bit of another, and the one that you only have a little bit of will limit how much you can make. So for example, if we were trying to make bicycles, and so every bicycle, okay, that's the body of a bicycle. I know it looks sort of like, I don't know what it looks like, but it's pretty bad. Okay, and then each bicycle has two wheels, right? So say we had, let me get rid of the wheels and put them separately because we're going to build our bicycles. So there's our body again. I know, don't laugh too hard. And here's a wheel. So we have 5 bodies. So you would think, okay, great, I could make 5 bicycles. And I have 8 wheels. Remembering that we need 2 wheels for every bicycle, right? So looking at the bodies, we could make 5 bicycles. But looking at the wheels, we can only make 4 bicycles. So how many bicycles, total bicycles? So here's our bicycle again. Goodness, I'm a horrible drawer. So there's our bicycle. How many bicycles can we make? We can only make 4 bicycles. What limited the number of bicycles we could make? The number of wheels, right? This limited the number of bicycles we make. And we have 1 remaining, so we have 1 body in excess. Okay, so that's what we mean by limiting reagent. In this case, again, the wheel limited the number of bicycles we could make. All right, so the limiting reagent or reactant, some things you need to know. So first of all, it's the reactant that is completely used up. Okay, so in our BCA table, in the A section, it will be the one that ends up being 0. Okay. The limiting reagent limits the amount of other reactants that can participate in the reaction. Okay, like our bicycle example. Even though we had 5 bodies, the number of wheels limited how many bodies we could actually use. The limiting reagent limits the amount of products we can make. Again, thinking about our bicycles, even though we had 5 bodies with 8 wheels, we could only make 4 bicycles, our product. And the reaction stops when the limiting reagent is used up, even if we have more of other reactants. Once the limiting has been used up, the reaction is over. So there are some characteristics of a limiting reagent. And the excess reagent or excess reactant is the one that is not used up. Okay, there'll be stuff remaining. There'll be stuff after the reaction, the excess reactant, there'll be stuff left over, like our bicycle body. It was in excess, we had 1 left over. Okay, let's go through the steps on how to determine the limiting reagent or limiting reactant. Good news is it's not much different than what we've been doing with our basic stoichiometry. There's just one major step different. So the first thing we're going to do, just like we've been doing, is fill out the before row, keeping in mind that before means before the reaction has even started. You're going to use the amount of reactants in moles. Moles is really important, given in the problem. If you're given mass, right? If you're given mass as you're known, you first have to convert to moles and then use the table. And the products are going to be 0. because it's before the reaction has started, so we haven't actually produced anything yet. Okay, now we get to the new stuff, so attend, really think about this. So to determine which reactant is limiting, you are going to divide the moles given in the problem, or calculated from the mass, by its coefficient from the balanced equation. So again, you're going to divide the moles given in the problem by its coefficient in the balanced equation. And the smallest number from step 4 will be the limiting reactant, and that is the one we're going to use as the given. Okay, so the smallest number is the one we're going to use as our given. And the amount of product formed from the limiting reagent is the maximum amount of product that can be formed. And any leftover reactant is going to be the excess reactant. Okay, so it sounds a little bit weird. It's actually not too bad. So let's now try going through one of these. All right, so our sample problem, we have 2 grams of ammonia is mixed with 4 grams of oxygen, which is limiting reagent. What mass of NO is produced, how much excess reagent remains. Okay, so the very first thing we need to do is put our balanced equation in our BCA table. So we're going to have 4NH3 plus 5O2 producing 4NO plus 6H2O. And then we'll divide these up. All right, so now if we look at our given, we're given grams of ammonia and we're given grams of oxygen. So first thing we're going to need to do is turn that into moles. Let's start with the ammonia. By the way, ammonia is NH3. So we have 2 grams of ammonia. So 2.00 grams of ammonia equals X moles of ammonia. And this is a basic mole conversion problem, so we'll set up the grid right in our given. And now we need to find an equality that has the units grams and moles in it. And that would be 1 mole of ammonia equals the molar mass of the ammonia, which remember you get off the periodic table. So it would be the mass of 1 nitrogen, which is 14.01 grams, the mass of 3 hydrogens, each of which is 1.01 grams. So that gives us 17.04 grams of ammonia. Okay, and now we're going to put these in the grid, setting them up so our units cancel out, which means we need to put the 17.04 grams on the bottom and the 1 mole on the top. Double check that we set this up right. Grams ammonia crosses out grams ammonia. So now we need to multiply and divide. And using the correct number of sig figs, if I did my math correctly, I came up with 0.117 moles of ammonia. And now this number we can put into our BCA table. So we've got our 0.117 moles of ammonia now in our BCA table. We have to do this again for oxygen because we have 4 grams of oxygen. So 4 grams oxygen, oxygen remember is O2, equals X moles of oxygen. And setting up our grid, we'll start with our given 4 grams of oxygen over 1. And we're going to again use our equality 1 mole, but this time of oxygen equals the molar mass of oxygen. Oxygen is 16.00 grams, but there are 2 of us, 2 of them. 32, and remember there's 2 digits after the decimal, so 32.00 grams of oxygen. Okay, so now we need to take these 2, put them in our grid, setting them up so our units cancel out, which puts our mass at the bottom again, and our mole at the top, and grams O2 crosses out grams O2. So when we multiply and divide, we're going to end up with 3 sig figs, and if I did this correctly, I got 0.125 mole of O2. And this number can go in our grid for the O2 section. Okay, let's put our starting moles in our BCA table. So we have 0.125. Did I get that right? Moles of O2. All right, so all of this so far we've done before, but now what we need to do is figure out which is limiting. And remember, to figure that out, we need to, right here, divide our moles by its coefficient. So for NH3, we're going to use 0.117 moles divided by its coefficient, which is 4. So divided by 4, and I got 0.02925 or 293. And for oxygen, I'll do it over here on the other side. We have 0.125 moles, and its coefficient is 5. So we're going to divide that by 5. And I got 0.025. All right, so what do we do with this information? Let's go back and check real quick. The smallest number is the one that's limiting, and it's going to be our given. So which one was the smaller one? Let's see, we've got NH3, which is 0.2925, and oxygen, which is the smaller one, right? It's 0.025. So oxygen is going to be our given. We're still going to keep NH4 there. We're not going to say 0 because we have 0.117 moles. But when it comes to the mole ratio now, which one are we going to use? We're going to use the coefficient for oxygen. Okay, so everything else we do from here, we've done before. We're going to set up our mole ratio, which is going to be, on the top is going to be the coefficient for each column. So 4 for NH3, and 5 for oxygen, and 4 for NO, and 6 for water. And then the bottom number is the coefficient for our given, which we decided was oxygen because it's the limiting. So 5 and 5 and 5 and 5. Okay, so before I move on, one thing I forgot to do, hopefully you shouted it out at me and I didn't hear it, is we need to fill our before, which is 0 and 0 for the products. Now the reactants we don't fill out right away because we don't know. Remember, the limiting is the one that we run out of. The excess, the other one, we don't. So now that we know what our limiting reagent is, we can say that this guy is 0. Because he's limiting, we're going to use them all up. We don't know about this one yet. We're actually going to have to calculate it. We're going to have to figure out the excess. Okay, so from here, we can now figure out our change. How did we get from this 0.125 to 0? Well, we had to lose, let's try this again, I got this. We had to lose negative 0.125, right? So our change factor is going to be 0.125, negative for the reactants because we're using them. So the same with this one. And then positive for the products because we're gaining that much. Okay, so now we just have to figure out, we have to calculate the change for ammonia and NO and water. Okay, so for ammonia, we're going to multiply 4 over 5 by negative 0.125, and that gives us negative 0.1 is what my calculator said. However, we know there's 3 sig figs, so we're going to add 2 more zeros there. We've got the change for oxygen. For NO, again, we're going to multiply 4 divided over 5 times 0.125. And again, my calculator told me it was 0.1, positive this time, but we need 3 sig figs. And for water, we're going to multiply 6 over 5 by 0.125. And my calculator said 0.15. But again, we need to add a 0 in there for 3 sig figs. Okay, last step is to figure out the after amounts. So remember that after is going to be, trying to figure out how to write this, place to write it. I guess I'll write it down here. It's before minus change equals after. Okay, before minus change equals after. So starting with NH3, we started with 0.117 moles. We used 0.1 moles. So what's left over is 0.017 moles. For O2, we've already got that. For NO, we started with 0. We got to 0.1. So our after is going to be 0.100. And by the way, after is before plus change. Let's change that. Before plus change equals after. Got that? Because I have to erase it to leave some room. And the last one we started with 0. Our change was 0.150. So we made 0.150 moles of water. All right, let's go back to our question and see what kind of things we're supposed to answer. So the first question is, which is the limiting reactant? Well, the limiting is the one that got used up all the way, and that would be the oxygen. So limiting reactant is oxygen. Okay, what's our next question? What mass of NO is produced? All right, well, it looks like we have to do a little bit of work with that one because remember this is in moles, but we know we produced 0.100 mole of NO, so we know how to do this. 0.100 mole NO equals X grams NO. So write our grid. And then we need an equality that has the units mole and grams in it. And that would be 1 mole NO equals 30.01 grams NO. We set this up in the grid, one in each spot, setting it up so that units cancel out, and this time moles goes on the bottom, and 30.01 grams goes on the top, moles cross out. So when we multiply across the top with the correct number of sig figs, which is 3, we get 3.00 grams NO. So the second question was how much NO could be produced, and that would be right here, 3.00 grams NO. And the last question we have here is how much excess reactant remains. Well, our excess reactant is this guy here, and there is 0.017 grams remaining. So let's make a little room here. There you go. So 0.017 grams of NH3. Oh, wait. Not grams. Moles remain. Now, being that everything else is in, how do I say this? In mass, we should probably go ahead and change this to mass as well. So we can do that real quick. So we're going to have, let's just take away the remain, equals X grams NH3. So we'll have 0.017 mole NH3 over 1. We'll use the equality 1 mole NH3 equals the molar mass of NH3, which we solved earlier, which was 17.04 grams. We will put 1 mole on the bottom and 17.04 grams on the top. And when we multiply, we get 0.28968 grams. We only need 3 sig figs, so 0.300 grams NH3. Okay, we're almost done. I just want to point out one more thing. Another good question I could ask you is how much of the excess reactant was used. Where would that information come from? Well, that would be the change area. This area here, that would be moles. You could change that obviously to mass, and that would be how much was used. Okay, folks, that's it for today. Have a good one.